Alright, so for this lesson, I want to talk about some of the pitfalls of linear regression. Two things you should be looking out for. One of them is about extrapolation. The other is about outliers. Since both of them can give you some pretty bad answers if you're not paying attention. So my first lesson is don't extrapolate. Since you have checked the correlation and constructed a linear model, then it can be used to approximate the relationship between the two variables. However, these models have real limitations. Truth is always much more complex than the one simple line. So for instance, using a model to make predictions outside the range of our data, this is called extrapolation, can give false answers because we do not know how the data outside our limited window will behave. So this means we should exercise extreme caution about making any predictions that go outside the range of our x values. So our linear models are really only good between our minimum and maximum x values. Anything beyond that is speculation. So let me start with an extreme example here. If Beth is getting married today, then it stands to reason we have the following data. That yesterday, day 0, she had 0 husbands. Today, day 1, she had 1 husband. Well, if we were to extrapolate, extend this out, day 2, she should have 2 husbands. Day 3, she'd have 3 husbands. On day 60, in terms of the equation, it looks like the x and y values are the same. So my equation is basically y equals x. But stands to reason, day 0, she has 0 husbands. Day 1, she has 1 husband. Day 2, 2 husbands, and so forth. So on day 60, if this equation was true, day 60 she would have 60 husbands. Okay. Bit extreme, but this is an extrapolation. Our data is really only good between day 0 and day 1, if that far. It's really not good for day 60. Not even good for day 2. Well, let's try another one. Below are the monthly average high temperatures for Yakima, given by month. Let's find a linear function that models the data and interpret the slope and the intercept. And then, can this model be used to predict temperatures for November? Well, we go from January through July. So, searching that last question, we could already answer. At least I hope you can. No, you can't use that for November. We're only good between January and July, month 1 up to month 7. But to create a model, stat, enter, I'd enter, list 1, 1, 2, 3, 3. Okay, so there's the months. And the temperatures, January, February. Back up. 4, 7. There you go. 64, 72, 80, 88. Double check. 80, 80, 72, 64, 56. Okay, I think that looks good. So stat, scroll over the test, and then move to linreg t-test. And let's see here, list 1, list 2. I don't really care about the hypothesis test right now. Enter. Alright, so you see at the very top you have y is equal to a plus bx. The a is the slope, and we're told slope is 31. No, that's going to be a is the intercept. So let's see here. My prediction for temperature is 31 and then plus 8.18 times the month. In this case, the 31 would basically be the temperature for month 0. That would be an extrapolation because we don't have a month 0 in my data set. I guess that would technically kind of mean December, but it's also an extrapolation. The 8.18 would be essentially the average increase in temperature per month. So from January to February to March to April, temperatures were going up about 8.18 degrees per month. I scroll down, you can see the correlation is 0.9999. So pretty close to zero. It's almost perfect. However, if I wanted to do November, if I did 31 1 plus 8.18 times 11, I would end up with the average temperature of 121 degrees. Typically, Yakima in November is in the 40s. This is a pretty good model from January to July. Terrible if you want to include November. There we go. All right, let's try another one. This table here shows the number of live births per 1,000 women aged 15 to 44 years in the United States. And then the independent variable being years after 1965. So the 0 here means 0 years after 1965, so that is 1965. The 1.5 would represent 1970. This would be 1975, 1980, 1985, 1990, 1995, and up to 1999. So we're really good between the years 1965 and 1999. But I want to find the correlation and the equation. So stat, enter. So here, I should just be able to overwrite these. 0, 10. Whoops, I'm missing something, aren't I? 0, 5, 10. 15, there we go. 20, 25, 30. Okay, so there's the years. 19.4, 18.4. Not coming out right, are they? See here, got 19.4, 18.4, 14.8. Okay. There we go. And there. Okay. So stat, test, up. All right, correlation. Negative 0.7812. Okay, so decent. If you look at the scatter plot, you'll find it's a little bit of a curve to it, but it's reasonably linear. We want to find the equation. The prediction for rate is we have 18.2 minus 0.116 times the year. Okay. In this case, the 18.2 would represent our prediction for the year 0. So for 1965, we got 18.2, and you can see that's a little bit low from the actual number, but reasonable. Negative 0.116. That's going to be the decrease in the rate per year on average. So some years may be higher, some years lower. On average, the rate's been decreasing by 0.116 per year. All right, so let's estimate the birth rate for 1978. So 1978, that would be 13 years after 1965, so that'll be year 13. Again, we do subtract 1965 from that. You'll get the year we need. So we have the rate would be, I'd put in the 18.2, then minus 0.116 times 13. Times 13. And I get for the rate about 16.7. And for 13 would have been right here in the table. Seems a little bit high, but not too far off. Let's try that again. One more. Use a model in Part B to predict the birth rate for the year 2150. So again, if I subtract 1965 from that, I will get my year to be, I'll see here, 2150 minus 1965. I get 185. All right, so what do you have? My rate, let's say 18.2 minus 0.116 times 185. So 18.2 minus 0.116 times 185. All right, we end up with negative 3.26, which I suppose means that sometime in the next century, the babies are going to be coming back into the womb. Maybe not. This would be an extrapolation. I really have no faith at all in this prediction, and obviously it can't be true. And I'll stop there.